Hello, good morning from Troy, Michigan. Going to show everyone today how I put together this very simple, very inexpensive square resistance probe. You want to measure square resistance if you're interested in the conductivity slash resistivity of surfaces. So if you're into conductive materials, paints, inks, supercapacitors, frequently you're going to have some type of material coating, and you want to know what the resistivity is. Typically you're looking for something as conductive as possible, as low as resistance as possible. So with this type of probe, take your material that you want to measure. The probe is just hooked up to an ohm meter. Place it on there, and you've got a calibrated reading of the surface resistivity. There it's showing 23.5, 24.2. It's a little bit sensitive to this surface here. It's a little bumpy, so depending on the pressure you can get small changes in the readings. Right there it's 19, 25, 25 ohms. The key to measuring square resistance is somewhat defined right in its name. You have a square conductor, actually conductive just on two edges. This edge on my particular probe is 25 meters long, 25 millimeters long, 25 millimeters in length on this side, and then the spacing between this inner edge and this inner edge is also that exact same 25 millimeters. It doesn't have to be 25 as long as the length of this conductor, and the gap between them is the same. So it could be 15, 20, 100 millimeters, depending on what's convenient for the type of material that you want to measure. So let me show you how I designed and built this, and maybe for some of you it'll work out. You can do your own. Out on Thingiverse, I've put the CAD files. Actually, it's just one file. You need to make 4 of these little pieces here. These I cut out on my laser cutter. I'll stick a little insert in here showing them being cut. But the file is designed for 3 millimeter material. That particular file will only work on 3 millimeter material because the holes here that have to mate with these tabs are based on the thickness of that material. You need 4 of these pieces. They're all the same. They're identical. And you'll notice a little bit of difference here between the length of this tab and this tab. That makes sure that it's kind of foolproof when you put it together. So it goes together like this. It will not go together the wrong way. It only goes together one way. The key to the probe, I'll show you that on the finished probe, is to having this edge here proud of this edge. So this is going to be the conductive part of one side of the probe, and when you place it on the material that you're measuring, it guarantees that only the conductive material, not the rest of the frame, is going to contact the material under test. So taking 4 of these probes, the first thing you want to do is to decide on a conductor. This was designed for inexpensive, readily available kitchen foil. The heavy-duty variety here is a little bit easier to work with. So basically, you'll take a piece of this, using one of the little plates as a template. You're going to cut out 2 strips of that material the exact width of that template so that it's going to line up with the length of the probe. Okay, so we've got two of these cut, and then what we want to do is to take two of these probes here, and we're going to wrap that around like this. Hopefully I've got the camera lined up where you can see that. I'm going to trim this off a little bit. That's not critical. Okay, now the thing that you want to note is that the length of one of these probe sides is the same as the aluminum foil we cut, because we use this as a template. Okay, and then we're going to take our two of the four that we've wrapped with the aluminum foil, and we're going to start assembling here. Let's see, what do we got? Okay, we've got these two and these two. The way this goes together is with the tin foil on the outside. So that there we go. Gotta make sure we've got the narrow slots lined up with the narrow tabs. And like that, like that, like that. Okay. There we go. Yep. Sorry, that looked a little cumbersome, but maybe you're a little more dexterous, a little more dexterity than these old fingers. Okay, so let me point out. We've got the two conductive surfaces, 25 millimeters long, spaced 25 millimeters apart. On this side, this top edge is proud of this by about a millimeter or so, so that this contacts the surface and the rest of the frame doesn't. On this side, since these pieces are identical, we've got a little recess. So obviously this is the top and this is the side that'll be contacting the surface. Now when you go to put this together for the final assembly, you've got a couple little options. Basically, everything is held together with one screw. So take one screw, put it through there, put it through there, and there you go. Now, those of you that are looking closely at what I'm doing, I'm sure are thinking, wait a minute, that's not going to work. You've got a screw clamping this together, holds it nice and firm, but obviously the screw is going to short out this side to that side, so you got a couple options here. One, whether it's an 832 or about a 4 millimeter nylon screw, that solves the problem. So one option is just use a non-conducting plastic screw. Nylon 832 screws are readily available in the U.S. and I suspect something around 4 millimeter in the rest of the world. Or what I did, I had these little shoulder washers, little grommets available, so I can pop that in the hole. Now go ahead with my 632 screw and drop that in, and now the screw clamping one side to the other doesn't short out the two sides. So here in the fully assembled unit, maybe you can see it, right there is the little shoulder washer underneath this nut, and the same thing underneath the head of this screw. To make electrical contact to the two sides of the probe, I just used a couple ring terminals. In this case, the ring terminal sits on top of the foil. The contact for this side, the same on the other. Push through the shoulder washer to make sure that the screw is not shorting out to the foil of the ring terminal. Same thing here, shoulder washer. separating the nut and the rest of the bolt. Okay, so anyway, this thing goes together fairly simply. A little bit tricky to fold that foil and clamp it, but let's take a couple readings and see what we get. So we started out with this piece here. My not very good conductive carbons are about 33 ohms per square. Obviously the tinfoil itself is going to show me what the contact resistance is of the complete circuit. So here you've got the resistance of the foil, the contacts here, the actual meter connection. So from whatever reading we take, we can subtract 0.9 ohms per square. In one of my earlier videos, I showed how I make some of my current collectors. This is a 5.7 ounce twill weave carbon fabric. It's nothing special. It's the same stuff that is used now in the automotive industry and many industries, not unlike fiberglass cloth and epoxy resin to make boat holes. But the neat property of the carbon cloth is it's actually fairly conductive. It's hard to work with because, as you can see here, it frays. But if I take a strip of this, put a nice little piece of really sticky tape on the back, and then cut it out to the shape of the tape, now it's quite stable. It doesn't ravel, can easily bend it, flex it, and it works fine. But anyway, one of my earlier videos showed the process to make these little test strips. What kind of resistance do we get here? So 2.4 ohms, 2.5 ohms square. It's somewhat dependent on how much you push down, because now I'm sinking the surfaces of the probe into the cloth, but that's 2.2 ohms, and that's really good. One of the things that made it really good, though, is the fact that I took the fabric as received, and here's a piece of it just off the shelf, if you will. It's about 4 ohms, 4.2, depending on push a little bit, 3.9. If you take this material, put it in an oven, actually you probably have to use a kiln because of the higher temperatures. Put it in the oven for about 360 to 400 degrees centigrade for an hour. You'll take the conductivity from the square resistance from in the 3 to 4 range. There we are, 4.1 down. Let's see which material is which now. Yeah, you'll take it down, just about half. Okay, so you can increase the conductivity, cut the resistance in half just by baking it in a kiln. There's 2 ohms right there. There's some carbon-coated paper. Oh, that's really a crummy carbon, 210 ohms square. That's not good for much other than taking nice white paper and making it black. Not a very good conductive ink. But anyway, I'll put these files out on Thingiverse. If you have any other questions or comments, feel free on YouTube to leave me a note. Thanks for watching. Bye.